In this video, we determine the energies and wave functions of the stationary states of a three-dimensional rectangular box. Let's define the rectangular box the following way. It extends from 0 to A along the x-axis, from 0 to B along the y-axis, and from 0 to Z along the z-axis. Since it is in 3 dimensions, this simple toy system is more realistic than the one-dimensional box. Inside the box, the potential energy function V of x, y, z is 0. Outside the box, V of x, y, z is positive infinity. We will now solve the time-independent Schrodinger equation for this box. It is h hat operating on psi of x, y, and z equals energy times psi of x, y, z. Here, psi is a three-dimensional wave function. It depends on x, on y, and z, on all three coordinates. The Hamilton operator inside the box contains only the kinetic energy term. It is given by h hat equals minus h bar squared over 2m times the sum of the second derivatives, partial d dx squared plus partial d dy squared plus partial d dz squared. The sum of second derivatives is called the Laplacian and usually indicated by an upside-down triangle squared, called nabla squared. H depends on all three coordinates, but it has a special structure. The three coordinates occur in separate terms of the sum. This allows us to apply the separation of variables principle. If the operator is a sum of three terms, the solution is going to be a product of three terms, each depending on one variable. With this separation of variables, we write a product function. Psi of x, y, z equals some uppercase x function of x times some uppercase y function of y times some uppercase z function of z. Uppercase x, y, and z are functions that we need to determine. Inserting this into the Schrodinger equation and taking the derivatives where we can, this gives minus h bar squared over 2m times y z d squared x over dx squared plus x z d squared of y dy squared plus x y d squared z of dz squared equals e times x, y, z. Next, we divide left and right by x, y, z. This yields minus h bar squared over 2m times 1 over x times d squared x dx squared plus 1 over uppercase y times d squared of y dy squared plus 1 over z times d squared z divided by dz squared equals e. Now comes the crucial step of reasoning. The right-hand side is a constant, but the left-hand side contains three terms that each depend on one variable. Clearly, if we change one variable, say x, this could potentially change only one term, the first one that depends on x. But the equation tells us that the overall sum of the left-hand side must remain constant. Therefore, each term on the left must be a constant by itself. We can break the overall constant down into three parts and write e equals ex plus ey plus ez. With this, we can break the equation up into three separate equations. The equation for x reads minus h bar squared over 2m times 1 over x d squared of x dx squared equals ex. Multiplying left and right by x, this gives minus h bar squared over 2m times d squared of x dx squared equals ex times uppercase x. Now, this is exactly the Schrodinger equation for a particle in a one-dimensional box along x. Recall that the box length along x was a. We've solved this equation already, so we can write down the solutions. The energies are E of nx equals h squared over 8ma squared times nx squared. We have labeled the quantum number nx to indicate that it relates to the x dimension. The corresponding energy eigenfunctions are uppercase x of nx subscript equals the square root of 2 over a times the sine of nx pi x over a. Similar solutions are obtained for the other two functions. Uppercase y of y and uppercase z of z. Overall, the total wave function is the product of the three, as shown here on the left, and it can be written as psi of nx, ny, and nz, function of x, y, and z, equals the square root over 8 divided by a times b times c times the sine of nx pi x over a times the sine of ny pi y over b times the sine of nz pi z over c. The total energies are E of nx, ny, and nz equals h squared over 8m times nx squared over a squared plus ny squared over b squared plus nz squared over c squared. Clearly, both psi and E depend on three quantum numbers, one for each dimension or degree of freedom. In order to check whether the wave functions are normalized, you need to evaluate the normalization integral. You need to evaluate the triple integral over all space of psi star psi, dx, dy, dz. When you evaluate it, you will find that it is equal to 1, and therefore the wave functions are indeed normalized. Additionally, two different wave functions are orthogonal, as one can check easily by evaluating the corresponding integral. This is all for the three-dimensional box. We can apply all of the above to a two-dimensional box. Let's define the two-dimensional box to extend from 0 to a along x and from 0 to b along y. Again, the potential inside v of x comma y equals 0, and on the outside the potential v of x and y equals plus infinity. In analogy to the solution above, the solutions here depend on two quantum numbers, one for each of the dimensions. The wave functions for the stationary states are psi of nx and ny as a function of x and y equals the square root of 4 divided by ab times sine of nx pi x over a times sine of ny pi y over b. The energies are E of nx and ny equals h squared over 8m times nx squared over a squared plus ny squared over b squared.